The first thing we're going to look at in this review is what's the difference between series circuits and parallel circuits, and how resistances, voltages, and currents are changed and how they work in these different circuit types. So first, with series circuits, the resistances add together. R1 plus R2 plus R3, all of them together is going to equal to the total resistance. In parallel, the reciprocals add together. 1 over R1 plus 1 over R2 plus 1 over R3 is all going to add together to give you the total resistance. When we get to voltages and currents, we've not, to this point, had explicit formulas, but I'm going to actually write these down in formulas so you can see what we're talking about. So in series circuits, all of our voltages are going to be equal to the total voltage. So the voltage drop over the first resistor plus the voltage drop of the next resistor all together is going to be our total resistance. This happens because once we go through our whole circuit and are back at the negative terminal of our battery, we know we have to end up with 0 volts. So with that total 0 voltage, we need to be dropping all of that voltage that we start with. So if we start with a 5-volt battery, we need to drop those 5 volts along the way and end up with 0 volts. In parallel, we know that the voltages are all equal to each other. So the voltage drop across the first first resistor is equal to the voltage drop across the second resistor, which are all equal to the total voltage. In current, this idea changes. So for a series circuit, the total current is equal to the current through each of our resistors, whereas in parallel, the total current is equal to the sum of all of the individual currents. You all may recognize that what we do with voltages in series, how we deal with them, is how we deal with currents in parallel, and vice versa. How we deal with currents in series is how we deal with voltages in parallel. This can be helpful if you remember it this way. That way you only have to remember what we do in series and then flip it for parallel, or something like that. As long as you keep straight how we deal with voltages and currents in parallel and in series. So let's try to see how these work in an actual application. Because a lot of you have been having trouble with combination circuits, I'm going to do a really in-depth view of how I solve this simple combination circuit here on the right. So let's get started. So first we're going to start with this circuit here on the right, where we have a parallel circuit. So we come out of the 6 volts, right? We hit this junction right here. So we know that there's going to be a parallel circuit, because this is the way parallel circuits are, where we have a path where we can either go across the top or we can go across the bottom. However, inside this parallel circuit, we have this series circuit right here, the 50 ohms and the 200 ohms. This series circuit is inside the greater structure of the parallel circuit. So because the series circuit is inside the structure of the parallel circuit, we're going to start by trying to solve this series circuit. So let's combine these two resistors together, a 250 ohm total equivalent resistance of those two. So we can redraw our circuit in such a way that we just replace those resistors with the equivalent resistance. So this drawing up here in blue is essentially what we're going to imagine is replacing our parallel circuit here. We have a 250 ohm resistor and a 50 ohm resistor. Now we have to look at how we add together these parallel resistances. So we do the reciprocal adding and we end up with 1 over R is equal to 3 over 500. This gives us a total resistance of 166.7 ohms. So when we do this combination, when we get this all down so we have an equivalent resistance, the only thing we use that for is to find the total resistance. Once we've found the total resistance, we want to go back and look at our original circuit. So let's clean things up a bit. Much better. So we have this total resistance of 166.7 ohms. We have a 6 volt voltage source, so now we need to find the current. Using V equals IR, we can solve for our current. Let's take a moment to clean this up again and make it so we have a lot of space to start solving the rest of the problem. Because now we can zoom back out. We have the total resistance, we have the total current. Let's look at the voltage and the current through each resistor. Just as a side note, I want to take a moment to also clarify what I mean by the total current. The total current is the current that is coming out of the battery. So it's the current at this point here. It's not necessarily the current through each of the resistors because we have these in parallel. So some of the current is going to come out of the battery here, but it's going to split. Some's going to go north, some's going to go south, and so we're going to have some on each of these branches here. Because of the way this current splits, we can't necessarily solve this problem right away with just the current. We have to look at what happens with our voltages. We've exhausted everything we can do about our resistances, we've exhausted everything we can do about our current, so let's look at our voltages. What do we know about voltage of resistors in parallel? Because that's the first thing we deal with, this parallel split. We know that our total voltage of 6 volts is going to drop across both our lower branch and our upper branch. So our lower branch, with just the one resistor dropping 6 volts, that's something we can solve, so let's do it. So we found that the current through our lower branch is going to be 0.012 amps. So this allows us to basically completely solve what's going on with this resistor here. Now we need to look at what's going on with our top branch. Now we know that the total voltage drop between these 2 points across these 2 resistors added together is going to give us 6. Because these are in series, the total voltage drop is going to be 6, so that's going to be 6 total. We know that the total voltage drop here is going to be 6 because these are in parallel right here, and so whatever the voltage drop across the top is going to be equal to the voltage drop across the bottom, which is going to be equal to our total voltage. So this total voltage here is going to be 6. But how do we know how much voltage drops over our first resistor compared to our second resistor? Let's take a look at our current. We know that the incoming current is going to be 0.036 right here, but then it splits. Some of it goes up, some of it goes down. So let's draw what this is going to look like. So we have 0.036 amps in. We know 0.012 goes down, so what goes up? Because the total current entering a junction has to equal the total current leaving a junction, that's one of Kirchhoff's rules, we know that this top resistor here is going to be, or top current here is going to be 0.024. So this voltage, this current, 0.024, is the current through the entire branch. Because that's the current coming into this branch, and because these two are in series, the current of the 50 ohm resistor is going to give us the current of the 200 ohm resistor. Again, let's clean up. Here I've labeled it IN for I in the north, the current through the northern branch, and IS for I in the southern branch, the current in the southern branch. So now we can figure out the individual voltage drops. Now we've already said that V500 is going to be 6 volts because that's the only resistor in its branch, in its loop, and so all of the voltage has to drop across that. But what about the 50 ohm and the 200 ohm resistor? Well, V50 is going to be our 0.024 times 50 ohms to get a 1.2 volt voltage drop. So V200, we can solve the same way, 0.024 times our 200 ohm resistance, or we can look at, okay, we have 6 volts, we've dropped 1.2, the remaining voltage has to drop. Either way, we end up with 4.8 volts is our voltage drop. And so now we've been able to show what the voltage drop of each resistor is, the current through each resistor up here, and the resistance total of the circuit and the total current of the circuit. So let's look at what we know about both series and parallel circuits and compare to those rules we had on slide 1 about what happens with currents, voltages, and resistances. We used the rules about resistance adding to get what our total resistance is, so that works. And when we looked at the current, we had our northern current of 0.024, our southern current of 0.012, and our total current is the sum of these two. So that is all consistent. Because they are in parallel, the currents should add together. Now, when we were talking about it, I kind of skipped over the fact that 50 and 200 ohm resistors in this one are in series, and so our current that we have through one of them, 0.024, is going to be the current through the entire branch. So that is consistent there. Now let's look at our voltages. First, we have to look at what is going on with our parallel circuit, because that's the first thing we run into. The voltage drop across the bottom rung, the bottom branch, if you will, is 6 volts, which is our total voltage, so that is consistent. And the voltage drop across the top, added together, they're in series, so we just add these two together. That gives us 6 volts, which is consistent, again, with what our total voltage drop should be. So all of this works out, and we get a consistent answer. So let's take a moment and talk a little bit about Kirchhoff's laws, because I feel like they're there when we do these explanations, but they might have gotten lost a little bit. So let's go and review those. So let's look at what's going on here on the left. We have 4 different wires coming together to form a junction. Now, the leftmost wire comes in with 2 amps, the topmost wire comes down with 3 amps, the rightmost wire exits with a 0.5 amp. What's going on with the bottom wire? So the first thing we need to figure out is which direction the current is going. Because we have more current coming in than current leaving, we know that our answer has to be leaving, because the total has to be equal. We have 5 amps in, a 0.5 amp out, so that means it has to be 4.5 amps leaving the circuit. What about over here on the right? This left one is the junction rule for Kirchhoff's laws. The right one is going to deal with the voltage drops. So we start with 10 volts. Our first resistor drops us 3 volts. Our second resistor drops us 2 volts. How much voltage drops across this mystery resistor? Well, we take our 10, subtract 3, subtract 2, and we get that our voltage drop is going to be question mark equals 5 volts. Now some of you might say, but Mr. Halberstadt, what about these resistors here? We can ignore them because they are not in the loop we're talking about. Now if we're talking about currents, we got to pay attention to those resistors. But when we're talking about voltage drops, we just pick one loop. This loop here, across this resistor, across this resistor, across this resistor, we can ignore these currents or these resistors over here. Don't got to pay attention to them. We just need to worry about the one loop that has our mystery resistor in it. So go on, flip to the next page. You'll have a nice quiz, and then we will talk tomorrow, and then our last test before spring break will be on Wednesday. Get excited. Does this quiz look familiar? First, what's the current coming out of a junction where you have 2 amps and 3 amps coming in, 0.5 amps leaving? What's the current coming out of that junction for the fourth part of the junction? And second, we have a 10 volt battery that provides voltage across 2 resistors. What is the voltage across the last resistor? Fill out your sheets, and I will see you on Tuesday.